you would like to see done. But I should have come around and checked them. I'll try to do that at some point.
Actually, it's just there's homework 6, right? Yeah, no, we didn't have. No.
Wait, so we're up to 7, right? Like we.
Oh, we got 7 on the list, so. Well, 7's the one we didn't have on my time for today.
Oh wait, really? Oh shoot.
Yeah.
Did you already do 7?
Yeah.
7's today, so
Okay.
yep.
Well, that's good.
Fought your way through it. Questions on anything up through 6?
Well,
No, we're good to go. Okay, so is anybody not taking physics in here? Okay, so I don't know how much you've done with vectors, but we're going to talk about that. So it's 12.1 in our book, and we're going to talk about the geometric representation of vectors, and then we're going to talk about the algebraic representation of vectors. So when, in my experience anyway, when I think back, when the first I worked with vectors, I found them to be a little confusing. So stop me and ask me if something's not clear. But what happens is some quantities sort of work well just being represented by numbers, things that are like time or speed or distance, that kind of thing. But others, you need more. You need a quantity, a magnitude, and a direction. Things like acceleration, velocity, things like force is a big one that we'll talk about a lot in here. So what we do is we represent them with directed line segments. And we use this little kind of half arrow symbol above it to represent that, or sometimes it might be represented with initial point and a terminal point, and it might be called, the vector PQ. So when it's named with 2 letters, the order makes a big difference. So vector PQ starts at P, called an initial point, and ends at Q, called a terminal point. And PQ goes the opposite direction, and direction matters in vectors. Now, what I think is kind of tricky is you have to get used to the idea of these are slidable. So the idea is you can move a vector around in the plane when it suits your needs. And so if you have another vector, I'm going to try to draw one over here that's the same length and the same direction. I'm going to call that vector U. So vectors that have the same length, which we'll call magnitude, and the same direction are equivalent. And so if I did that correctly, we could see that V and U are equivalent. They are equal to each other. They have the same magnitude and the same direction. And so we represent this. So we call the magnitude or length of a vector is represented. It depends on which book you use. So some books like ours is going to use just a single bar here, which is also the absolute value. So it is an absolute value sign, and it can also be referred to as the absolute value. So others, you may see it also written with the double bars there, and I may get carried away and inadvertently sometimes write it this way, but our book is going to use just the single bar notation. But these mean the same thing, just depends on the author of your book. And it will refer to, the direction will be given by an angle when you insert an x-axis on there. And so we're going to get a direction, usually represented by an angle, and then a magnitude or length. So we show that visually, geometrically, we show a longer vector has greater magnitude. And so in the case of, if this was a velocity, then the magnitude might be it would be its speed. Okay, it would be as miles per hour. And if this was like a force, it might be measured in English measure with pounds. And so this might be, 8 pounds, and that may be 5 pounds of force. And by the longer vector means it has a greater magnitude. Okay? And so then we can show visually how we add and subtract these vectors. So, and we'll talk about what this means also algebraically in a little bit. So to add and subtract vectors, if we have one vector, I'm going to say that's the vector v, and then we have another vector, say over here, that is vector w. And if we're interested in adding those together, we remember that they're slidable. So we take this orange vector w, and we sometimes call this the tip where the arrow is, and that the tail. And so if we move these so that they are tip to tail, so if I slide that vector w so that the tip of v matches the tail of w, then if we start at the tail of the beginning one and kind of like walking a path, we end up with the tip of the last one, then this vector here that starts at the beginning and ends at the end is that vector v plus w. So we show addition of vectors by moving them, we say, tip to tail. And a sum of vectors is known as the resultant. So if they talk about finding the resultant, or what is the resultant, a resultant is the resulting vector after you add two together. It's the new vector formed by adding two vectors together. Then to subtract vectors, so if we look at this, say, v, and we want to subtract w from it, then what we do is, if this is our vector w, this orange is our vector w, then we think of this as being adding the opposite. So we're going to add the opposite vector. So we make the opposite vector by making the vector the same length, but pointing in the opposite direction. And so then again, we can slide w, or negative w, so that it lines up with, maybe make it this way. So now we have, here is our negative w here. So the same length that w was, but pointing in the opposite direction. And we slide it so that it goes tip to tail with v. And then that resultant, now we're just adding, so our resultant is going to be that vector v minus w. Is that okay? So there's a nice picture that goes with this. So sometimes you may hear it referred to as the parallelogram rule. So the parallelogram rule, or that adding and subtracting vectors follows the parallelogram rule. So the idea is if you take two vectors, so I'm going to say here's vector v, and then I'm going to say here is vector w. So if we put those two vectors so that they share the initial point, so they start with the beginning of vector v matches the beginning of vector w, then together those two vectors form a parallelogram. Let's see if I can do this. So now if we then remember that these vectors are slidable, so if we take the vector w and we slide it up, or recopy it onto there, now we see that we have gone tip to tail with v and w, and so the resultant, one of the diagonals of that parallelogram, is going to be the sum of v and w. So that is v plus w. Is that okay so far? Now, if I'm going to try to create a subtraction, but it's going to be a little bit roundabout. So I'm going to look at the negative of w here. So I'm just going to turn it around so it's the same length, but pointing in the opposite direction. I'm going to slide now the tip to tail with v. So now that vector negative w goes this way. And now you can see that if we go v plus a negative w, that's going to end up over here. So this vector is v minus w. And then remembering that these vectors are slidable, if I slide that back over here, it will be exactly this diagonal. So that is going to be v minus w. So what's intended by the parallelogram rule is to note that when you put two vectors to where they share the same initial point, then that will create a parallelogram. And one of the diagonals is the sum of those vectors, and the other diagonal is the difference in the vectors. And that's known as the parallelogram rule. Okay? So we then give so we have ordinary numbers like 3, -2, and so on. So ordinary numbers are called scalars, and then these vectors are going to be represented by, either a single letter with the little vector symbol above it, or like a vector PQ with that symbol above it. So we can multiply a scalar times a vector. And we kind of talked about that a little bit in terms of the negative. So if this is vector v, then the vector that is the same length but goes in the opposite direction is negative v. And if we say this is vector u, then the vector 2u is going to point in the same direction but be twice as long. And so it's going to be this vector right here. And similarly 3u and 5u and whatever.
What's your multiplication of vectors?
We are going to, so we are going to find out in here eventually how there's two different kinds of multiplication of vectors. One we're going to call a dot product, which will take two vectors and give you a scalar. And one's called the cross product, which will take two vectors and give you a new vector. So there's actually two different kinds of multiplication of vectors. And we're going to talk about that eventually in here. Now, that's not an AP topic at all. So we're wandering here. We're going on a walk.
And this is on AP?
Well, what happens, so what we're going to do, everything on the AB is on the AP test. And then we're going to we're going to do on our walk for about the first quarter. Then the second quarter, we're going to do like a blitz review of everything we did last year. But I'll sprinkle in occasionally some new topics that are, some will be BC topics and some will be not. But they'll just kind of fit in with the differentiation and integration that we're reviewing. And then we'll do, like in January, we'll do some problems that I guess technically could end up on the AP exam, but I think if it was, there would be mutiny from people because it's not specifically listed. But a lot of engineering colleges do things like work, fluid force, centroids, stuff like that engineering colleges want their students to know because that's what they're going to do in their kind of line of work, in their major, but aren't going to be probably on. And on the AP exam, they say they will have applications of derivatives and integrals, which you could make a case for what we're going to talk about with work and fluid force and so on are applications, but not typically. They never have asked something like that. And I think to put that on an AP question without warning people would not be considered fair. But we'll do that. Then it'll get really slow because we're going to do the C part of BC calculus, which is series. So we're going to talk about Taylor series and the Maclaurin series. That'll go really slow. And so that'll take us probably till maybe mid-March or something like that. And then right at the very end, we will do calculus of polars, parametrics, and vectors. And that's it, just those three things. And that'll go really quick. And that'll wrap up the new stuff. And then we'll do a review and we'll hopefully take the AP exam So yeah, so it's kind of like we bookend it. So we start out here just talking about a pre-calculus idea of polars, parametrics, and vectors. The vectors goes a little deeper than most, I think, pre-calculus would, and more than we would need for AP. And then we'll finish the year coming back and talking about how do you take a derivative of this polar curve? How do you integrate, this vector equation and stuff like that? So it's kind of bookended. So let's look at, so we talked about scalar multiplication. And let's look at maybe a challenging, I think. I was trying to get you to think in vectors because it's a little different, I think. So I'm going to call this a square. It's A, B, C, D. I'm going to name it. I'm going to tell you that this is side length 4. And feel free to jot any of this down in your notes. So then I'm going to ask you some questions. So I'm going to say A, B, C, D is a square. And then I'm going to ask you some questions and think about it a little bit. And then we'll come back and talk about it. So the vector CD is equal to, and then I'm going to say the magnitude of vector BC is equal to, and then the magnitude of AB plus BC is equal, and then we'll say the magnitude of AB plus the magnitude of BC. We talk about if those are the same or not. And then we'll say, what do we get with AB plus BC plus CD plus DA. And then finally, we'll say, if I can only read my writing there. I have to cheat using my glasses here. I'll come back. You can start thinking on that. I'll try to figure out what in fact I actually wrote here. With AD minus AB. And be careful. Remember, when you're saying what is this vector equal to, it's got to be equal to a vector. And when you're being asked what is the magnitude of this vector, your answer should be a number, a scalar. And so make sure we're thinking about that correctly. You ready, or do you need a minute? So the first one, the vector CD is equivalent to what other vector? Now remember, this starts at C, goes to D. So yeah, it matters. It would have to be BA, not AB. Okay, so it's going to be BA. Okay. The magnitude of vector BC is 4, because all these side lengths are 4. So that is its length. Its length is 4. That's what we mean by magnitude. Now, the magnitude of vector AB plus BC, so AB, so if we come, here's AB to BC, that's going to be this vector right here. So that's the diagonal on that square. And using a little Pythagorean theorem, that's going to be how much? Yeah, so it's going to be, right, so it's going to be a square root of, right over here, it's going to be a square root of 4 squared plus 4 squared. that's going to be 32, which is 16 times 2. So it's going to be 4 square root of 2. So different now, and this is going to be different, right? Because now the magnitude of AB is 4 plus the magnitude of BC, which is also 4. So they're different answers, right? Next one's weird. So if you go AB plus BC plus CD plus DA, and you just go tip to tail. So there's AB plus BC plus CD plus DA. Takes you right back where you started. What is that vector? It's actually just right there. Because you're going to connect where you started with where you ended. So it's a single point, which is known as the zero vector. So the zero vector is any just point. It's a vector of length 0, which means it's a point, and it's considered pointing in every direction.
Would we need to specify like if it is A?
You could. I don't know how you'd write that though. That's a good question. That's a great question. I don't have a good answer for that one. Yeah, I don't know if you could call that just A. So the question is, could you call it A? I don't know. I think that'll work, but I don't know. That's a good question. Because remember, they're movable. So the zero vector could be, it could be there, it could be there, it could be there, it could be there. So it could be anywhere. So good question. Okay, AD minus AB. Now you got to think a little bit, right? So I want to go minus AB. So here's AB. So minus AB is going to really be EA. And I want to go tip to tail with AD. So here's AD. So if I slide this over, and there is our minus AB right there. And so going AD minus AB is going to be this vector here. But I want to slide it back in where we can name it in this square. So sliding that is going to be this diagonal here. And so we are going to call that PD. Kind of crazy? Kind of fun in a weird way. Okay, so let's talk a little bit about, so that's what I got for geometric representation, and that's enough to do homework 7, I hope. And 12.2, I'm going to talk about the algebraic representation of vectors. So it connects with what we have been doing already with polars and with complex numbers. And you'll see, I hope, that there's just all these similarities. So we know that we can, if we have an XY axis, so if we're in the rectangulars, and you can think of a point as being just that ordered pair, but you can also think of it as a vector that goes from the origin, and the origin is often called just O. And so that point, xy, can also be considered the vector OP. And our book will generally, I think this adds to the confusion or the ambiguity of it. So our book usually writes vectors just using parentheses, and then from the context of the problem, then you know whether it's really intended to be a vector or the point. And a lot of times, the arithmetic or computation you do doesn't really matter anyway. But sometimes you will see it written, I think, more clearly, and these are called angle brackets, these little pointy brackets, which I think kind of helps you understand that it is in fact intended to be a vector. And then this notation would clarify as well if you named it. Now, also in this, remember, I mean, again, if you want to just think of this another way, the parallel is if we, instead of thinking of that as being an XY axis, if we thought of it as an Argon diagram, then we could say that this was really, you know, X was the real part of this, and then it would be XYI is that complex number. And so you see, you know, in rectangulars here, the ability to kind of flow between thinking of this as a point, thinking of it as a vector, or thinking of it as a complex number, and the similarities and connections are kind of ripe. And so from there, you know, we can move to the same idea, only now we can add in the idea of this being polar. And so what we're going to do is think of this as being a point in polar coordinates. We can think of it as being also a vector, again, in polars. And so as a vector, and let me call this O again, so as a vector, so here's our point, just r comma theta. The first value is the real part of it, that is the distance we go from the pole, and the theta is going to be that angle that we go counterclockwise from the polar axis or the positive x-axis. As a vector, remember, now we think more in terms of rectangulars, so this would be r cosine theta comma r sine theta, and we could write that either in parentheses or in those angle brackets, either way. Okay? And then likewise in as a complex number, then this is where we did that whole r cosine theta plus I sine theta, which we learned to love and appreciate in shortened form as r cis theta. So again, we go from, now with a different way of referring to it, now in polars, we can still talk about it as a point, as a vector, or as a complex number. Okay, so for example, now when we're given ordered pairs, so here's an example. We have a point A whose coordinates are -2, 4, and then we have a second point B, and its coordinates are 1, 1. Then we can find, we say, vector AB in component form. So that is, we're thinking of this vector as starting at point A and going to part B and going to point B. And so what we want then is, you know, how do we write that vector? And I'm going to use the angle brackets because I think that's more clear, even though our book will just use parentheses. So to find the x component, you know, we say, since it's starting at A and going to B, we say we go tip minus tail, is how you find that. So you take the x coordinate of the ending point, the terminal point, minus the x coordinate of the initial point, the beginning point. And that's going to give us that horizontal component. And then likewise, we'll take the ending y coordinate minus the beginning y coordinate. And that's going to be the component form, we say, of our vector, which is going to be 3, -3. And that's our vector AB. So, once we know what vector AB is in component form, can we find magnitude of AB. Do we know what we're doing on this? What's our strategy here? Yeah, it's Pythagorean Theorem. Yeah. So if we wherever this started, so, and let's just draw a picture here. So here's -2, 1, 2, 3, 4. Here's our point A, and 1, 1 is going to be here. There's our point B. So AB is this vector. Now, these are movable, so we can slide these and say there's our vector AB in what we call standard position, because now its initial point is at the origin. And so now you can see, you know, that this distance right here, which we're going to call the magnitude of AB, is that length right there. And that is going to be just the hypotenuse of the right triangle. So here's your side 3, and that's the -3. And so that magnitude is going to be the square root of that 3 squared plus -3 squared. And we get to the magnitude. Is that okay? Okay, so more challenging is, let's find the polar coordinates. So you got to find the r and the theta. I guess that's not too hard.
So r equals like 3 raised to 2, and then theta would be like 75, right? Or no, 75.
Yeah. And we can do radians or degrees, either one. Did you hear what Alex said?
Yeah.
So we could say that, so there's our r, so we're going r theta. And we could do that angle as either radians or degrees there. So in radians, that would be a 7 pi over 4. And in degrees, it would be 315 degrees. Okay? And then if we wanted to represent it, let's say represent it as a complex number in polar form. So just to make that connection again with stuff we've already talked about in here. So there's not more work to do, it's just recognizing how to write it. How would you write that? Yeah. Yeah. So it's cis, because now it's cosine theta plus I sine theta, and that's how you get that imaginary part in there. Okay with that? Okay. So let's talk a little force. So a different kind of example here, but still we want to get the idea, get comfortable with writing forces as vectors, because we want to represent force with vectors. And again, this idea may be very different, especially for those that haven't done any physics. So a force F of, and I'm going to say, now this is metric measurement. That's N stands for newtons. And I found somewhere, now this is not something that means a lot to me, but a newton is the force needed, to bring one kilogram mass to a speed of 1 meter per second in 1 second. Whew, a lot of ones in there. So 1 kilogram, yeah, 1 kilogram mass to a speed of 1 meter per second in a second. So 1 kilogram is like 2.2 pounds. So you pick something up 2 pounds, you can move it about a yard in 1 second. That's the amount of force that is 1 Newton. It's kind of like you in the weight room, right? That's me benching. 2.2 pounds, 1 second. That's 1 Newton. Okay, anyway, back to our example. So a force of 10 newtons acts at an angle of 130 degrees with the positive x-axis, with positive x-axis. Can you find a force vector in component form? So we're trying to express the force as a vector. Does that make sense? I'll draw a picture. I don't know if that helps or not. Here's our XY axis. We're going to go 130 degrees, 90, so we're going to go, here is our vector. And its magnitude is 10. This is 130 degrees. And we want to write that force in component form. How do we do that? Let's take turns talking, not everybody at once.
So you could do like the reference angle. You could do like a tangent in so the tangent of 130 equals opposite over adjacent. Now, when you want to use like 50 cosine inverse or sine inverse, and then find one of
Now, I think you're making it harder than it needs to be. Can we just use this 130 degrees? Now, by using a reference angle, we'd have to artificially impose whether these are going to be positive or negative. But with the 130 degrees, taking a sine or cosine is going to put the correct positive or negative sign in there. Does that make sense? Okay, so can you pick it up from there? So what are we going to do?
And you could do like, sine of 130 equals opposite over hypotenuse, so opposite over 10. And so 10 sine 130 equals the opposite.
Good.
And then you could do cosine, so
Good.
and then 10 cosine 130 equals adjacent.
Follow what Alex is doing there? Okay, so, and this is sometimes called too, r cosine theta, which you may have seen, r sine theta, but the way you're thinking about it is exactly right. And so that's going to be r 10 cosine of 130 degrees and 10 sine of 130 degrees. Should you, you're going to throw in your calculator real quick just so we can see what that, get a feel for what that actually is.
7.660 and -6.428.
Negative, say it again.
-6.428.
Yep. And so as we would expect in quadrant 2, the x component is going to be negative, and then the y component is going to be positive. Okay? Okay, kind of an interesting question here. 2 minutes. We're going to use vectors to answer this. You can do it in other ways, but I think vectors is kind of a nice way to do it. So we're going to say A is the point 0, 4, and B is the point 6, 1, and we want to find the point that is 2/3 of the way from A to B. I'm flying here because of the time. So A is going to be 0, 4. There's A. B is going to be 6, 1. There's B. So we want the point that's going to be about 2/3 of the way from A to B. Okay, let's do this as a vector addition problem. Okay, so we're going to take this vector plus this vector to get, I call that OP. And OP is going to have the same coordinates as point P. And this vector AP, AP is going to be
2/3.
we want it 2/3 of the way from A to B. It's going to be 2/3 of AB. Okay, so we'll go OA plus 2/3 of AB. And that'll be a vector, but then we just drop the vector symbol and get the coordinates. All right. Very nice.